Alright, so we're moving on to worksheet 3, energy problems. So this is kind of the accumulation of what we've been doing with the bar diagrams and then calculating energies. Alright, so I'll kind of show you this one on scrap paper and show you how we do it first here. Alright, so 1 kilogram ball dropped from a height of 10 meters. How fast is the ball moving right before it hits the ground? Alright, so if we think about the bar diagrams, right, it's all PEG to start off. Right before it hits the ground, it's all KE. Alright, so if I made the bar diagrams, PEG, that was 4 units. Then at the bottom, it will be 4 units of KE. So what you can do here, call this location 1 and location 2. Well, PEG at location 1 has to equal the KE at 2. Alright? And from there, what we do is we plug in equations. Or we could solve for the gravitational energy we start off with, right? So mgh equals 1/2 mv squared. Now, as you get more sophisticated, you'll see these m's cancel, and you can do that, but I'll just do mgh right now. So 1 kilogram times 10 newtons per kilogram times a height of 10 meters equals 1/2 of 1 kilogram times v squared. Well, this is going to give us about 100 joules of initial gravitational energy. So if I was going to go back and figure that out, that'd be 100 joules. Well, then that means we have 100 joules of kinetic energy. So you can see why we can just set these equal to each other, right? Gravitational energy at the top equals the kinetic energy at the bottom. Alright, so you get a V, multiply both sides by 2. Alright, divide both sides by 1. And you get V equals the square root of 200 meters squared per second squared, which should be about 14 meters per second. Alright, so V equals 14 meters per second. And then, for the future parts of this problem, what you're going to do is double the height, see how many times faster the ball gets. Try to figure out how many times up higher to get 4 times the speed. Turns out, if you go back to this equation, right, and you solve it for V, alright, so mgh equals 1/2 mv squared. Cancel out the m's, multiply both sides by 2. 2gh equals v squared, or v equals the square root of 2gh. Because the h is under the radical, if you double the height, you don't actually double the velocity. If you double the height, you actually only increase the velocity by radical 2. You'd actually have to quadruple the height to double the velocity. It would be 4h, radical 4 is 2, you end up with twice the velocity. Let's see. Number 2 is very similar to number 1. I'm going to do one that has multiple energies. Yeah, number 4 is a good one. Oh, number 6 we're not going to fully do. Number 3 is a good one. There's lots of good ones. I think I'll make a different one up to kind of try to encompass multiple things happening here. Let's say, oh, I don't know. Let's do a spring one. Let's do it still going up the hill. So let's say we use a spring to launch a car up a ramp. Alright? Let's say it rolls up here about, oh, I don't know, 0.50 meters above its lowest position. Alright, and when it's there, it's still moving with a speed of 2.0 meters per second. Let's give it a mass of 0.50 kilograms. So we've got a cart. Let's say it was launched by a spring that was compressed. Oh, I don't know. X equals, we'll say 10 centimeters, 0.1 meters. K is going to be unknown here. So it's a half a kilogram car launched by a compressed spring. And we want to figure out what the spring constant is if it gets launched 0.5 meters off the ground and is moving at 2 meters per second. So if you think about the bar graphs, it starts off all spring potential energy, right? And then on the way up, that spring potential energy gets converted into PEG and KE. Now, we don't really know what the breakdown is. It's 50-50 or what, so they have to add up. And what that tells us, it basically gives us the equation that we're going to use, right? Because let's call this location 1 and location 2. So the spring energy at location 1 has to be equal to the PEG at 2 plus the kinetic energy at 2. All right, so I can't directly solve for the spring potential energy because I don't know K. So what I got to figure out is the total energy up here, and then I can solve for K. So you know what, I'm going to do that off to the side here first. I'm going to do that first. So mgh2 plus 1/2 mv2 squared. So it's gravitational energy at 2 plus the kinetic energy at 2. So now that's 0.50 kilograms times 10 newtons per kilogram times 0.50 meters plus 1/2 of 0.50 kilograms times 2.0 meters per second, and that whole thing's squared. So I'm going to go ahead and pound this out here. 0.5 times 10 times 0.5. It gives us 2.5 joules of gravitational. 0.5 times 0.5 times 4 gives me 1 joule of kinetic. So more gravitational. So I could go back and change this if I wanted to, right? But don't really need to. All right, so that's a total energy of 3.5 joules up there. Right, so our initial total spring energy is 3.5 joules. Right, so actually I'd probably have to make this 2.5 and reduce this down to 1.0, right? So take off the top of that. So that means 1/2 kx squared, which is just, just that formula there, has to equal 3.5 joules. So 1/2 times k, which is unknown, times 0.10 meters squared equals 3.5 joules. Now we're solving for k. So multiply both sides by 2. All right, you get k equals 7.0 divided by 0.10 squared. So 7 divided by 0.1 squared is 700. And spring constant will be newtons per meter. This is still joules up here. This is meters here. So you end up with units of joules per meter squared. Well, a joule is a newton times a meter divided by meter squared. Those cancel. End up with newtons per meter for the units on spring constant. So this is kind of an advanced problem, really. And it's not too bad. I mean, it's the total energy you start off with, which is all spring energy, equals the total energy you end up with, which is gravitational and kinetic added together. And really, all of these questions are kind of a combination of that. So, number 2 is just going from gravitational into kinetic, no friction. Number 3 is going from gravitational and kinetic. Speed at the bottom of the cart, well, what you got to do there is find the kinetic energy first. And that's going to be 80% of the initial, total, right? So I'm not going to ask you the intermediate step. I'm going to just jump to the speed at the bottom of the track, not the kinetic energy. But you have to know that you have to find the kinetic energy first, that there would be, and then solve for V. So whatever you get here, you know, whatever number you get here, that's got to be equal to 1/2 mv squared. This one here, we've got our cart launched up a 5-meter hill with a compressed 2 meters. Big, huge spring. This is actually the same spring we have in class. It might be a little too big, I don't remember. So it's going from spring. It's kind of like what we did here, right? It's going from spring into gravity and kinetic up here. But you know everything about the spring. You're going to be solving for V this time over on the right. This one here, it's going from spring energy, and you can actually skip the kinetic energy. You can just have it go from spring, and when it's at the top of its peak, it's all PEG. So it goes from PES to all PEG. So 1/2 kx squared. So you'd say PES, got it location 1, location 2. 1 equals PEG at location 2. 1/2 kx squared equals mgh2. That x is however far the spring's compressed, remember, and that's the height. So don't get those two mixed up, x and h. X is how far the spring is compressed. H is how high above its lowest point the block is gone. This one here, we haven't talked about work yet. We'll come back and look at 6 later on. But the amount of work done by friction is the buildup of internal energy, which you'd have to figure out first. And then coefficient of friction, that's a harder question. Anyhow, take a look at these, see what we can do. It's a fun unit in my opinion, because it goes back to those bar graphs really. So P, you know, total has to equal the total. Total initial has to equal total final.